So I had a request to go through 7, 8, 9, or 8, 9, 10 as well. Just because I think we kind of went over that really fast in class, super quick. So if you want to log on to the WebEx too, you can see the screen. Okay. All right. So let's just go through. Let me see your question. Maybe it's close. Okay.
Good morning, Neil.
Good morning.
We want to derive a first principles model for relationship between input voltage and output temperature. Okay, so let's just go ahead and run through that right now. No. Hey, Whitney, is your lab partner here? Okay. Is that Jay? Oh, okay. I figured it was Jay. Okay. You guys have a distinct advantage. Okay, you guys work together more time. You guys play together more than most lab partners. Although I'm not quite sure. You know, and my wife did electrical engineering, and she was often with the guys that she studied with a lot more than she was with me. I was just like, oh, you know, that's great. You know, you're a good study field. So, yeah, that's right. Anyway, there's an extra Arduino device here. Whitney, if you need it, there's also the computer and the Arduino device in the lab. If you need to go, you know, just use the Arduino device. So, and I also got all the mid-course feedback from you guys, which is really helpful. There's a couple things that you guys mentioned. I'll talk about this in class for you. You know, it's just like, you guys don't like kind of the difficulties with being able to log on to simulate and get that to work. You know, the time that you spend just to actually open up the program and get it to work, that's kind of a pain. And then also the Arduino headaches, you know. Anything that you guys are doing that's like not actually adding to your education value, you know, that. So I think that's something to try to work through and not cut out the lab. Well, I think the lab is super important. So if we can get past that, you know, the hardware, you get kind of beginning stages.
Hey, how's it going?
What's that?
The Vaclaw. Welcome back. Or welcome to. What?
So let's go through 8, 9, and 10. And yeah, you guys can't see other computers and just see the screen.
So you go in today?
Yeah, you guys
are. Man.
Are you logged in? Yeah. So just go to BYU.webex.com.
It's DK.
I'm just going to mute some of the microphones too.
They have like a grill.
Got some back talk. Okay. Okay. So let me just go through this, and if you guys have any questions along the way, we skipped a couple steps in class, so I don't want to skip any steps this time. I'm just going to go through it and, you know, just a measured pace, you know, go through all the steps with this. And you know, so we drew the process diagram before. You know, we have our board with our transistor, okay, and measurement device, okay, they're sticking into the board. And we kind of drew our box just around the measurement device and the, yeah, oh, it's a CHE 436. Don't connect to the audio part of it, because then we'll get some feedback in the room. Okay, so let me know when you're connected, Paul. Yeah, there's transistor and the thermistor. Okay, the thermistor is a little measurement device, and the transistor is the thing that produces the power, and you know, it has a voltage drop across it, and you get the temperature increase. Okay. Okay, so that's our schematic. We had a number of assumptions there. I'm just going to jump straight, you know, just remembering those assumptions. I'm just going to do the energy balance, generation, consumption. We said we had zero consumption, and this is going to be our, these are going to be our convective terms, and this is going to be our heating term in the device. Okay, so I'm just going to say that C sub P is constant. Okay, that was one of our assumptions. Equals, and then H, heat transfer coefficient, times A times, and then it was T ambient minus T, okay, because you had to get the signs right. So T ambient is greater, that quantity is positive, which means our temperature is going to increase. The slope is going to be positive on, if you just had this term. Okay, and then we also had something like alpha I times V. And I actually, Abe did a little bit more digging in terms of what the actual voltage drop is and stuff. You know, just assume that this is actually 0 to 255, and we said millivolts, but it's actually kind of like a percent open. Okay, so I'll just tell you guys this detail. You can use it if you want to or not, or you can just lump all of those extra constant terms into alpha. Okay. Either one. We said that this was 1 amp in class. That's actually not true. It's actually 9 amps. Okay, but 9 amps that are going through the device. But if you remember a transistor, okay, you have 3 inputs to the transistor, and there's a 9 volts delta V actually equals 9 volts, but or sorry, 9 amps, sorry, current equals 9 amps, but only 1.25 volts is being consumed across this when 9 amps. So a transistor, what it's doing is it's actually trying to be like a switch for something else, okay, to turn on or off another device that uses a lot more power, okay, but it actually has a perfectly efficient transistor would have no voltage drop across it. Okay, it's trying to deliver power to something else. It's like a switch, like a light switch. Okay, but there is a little bit of voltage drop across it, and that's why it heats up. Okay, and that's why we can use it for this lab. This is actually, if you have it at 255, it'll just stay on the whole time. If you have it at half of like 127, okay, what it'll do is it'll actually the pulse width modulation be on for 50% of the time. So it's either on or off, but it simulates the 255 is just going to be on all the time. If you have something like 50, you know, then it's going to be on and then off for a period. But it does that very fast, okay? So you guys don't even know it's happening, but it's like turning on for percentages. So I just want to tell you just a little bit about what's happening with that device. You know, if you just want to use 0 to 255 millivolts here and just lump all of that detail into your alpha, that's okay with me. You know, it can just be a constant times the voltage. Okay, that's perfectly fine. Okay, so let's just start with this, and we want to get a transfer function. We want to eventually get a transfer function T of S over T ambient, and then also T of S over V of S, okay? So we want to get both of those. And the question is, well, let's go ahead and go through this, but just keep that in mind. We want to get these two. So if we put a TA of S in, we get a T of S out. And if we put a V of S in, you can get a T of S out. And then you can combine those two and just add them to get your T of S from changes in ambient temperature or the voltage. Okay, like kind of like how we did with the additive properties of these things in parallel. Okay, so let me just start with that equation right up there. We need to get it in. We need to linearize it and put it, and then do the Laplace Transform of it. Okay, so let's go ahead and just linearize this. You can move the M sub Cp over if you want to. Okay, I'm just going to leave it on the left-hand side just because it's a constant. I don't necessarily need to move it over, but what I'm going to do is try to linearize the right-hand side of this expression. Okay, so I'm just going to call this f of TA, T, and B. Okay, so I have a function of those three things. And if I'm going to do a linear approximation, that's approximately f of TA bar, T bar, and B bar. And then I do plus df dTA, plug in my steady state conditions, and then I have TA minus TA bar. Okay, do you guys remember this from linearization? Okay, and then I do this for the other three as well. Okay, T steady state, T minus T bar, and then plus df dV, plug in my steady state conditions, B minus V bar. Okay, so let's go ahead and do that for our equation. I'm going to make this a little bit bigger here. Okay, so I've got this equation right here, and I want to go ahead and linearize the right-hand side of it. Okay, so let me just write that out down here again. MC sub P dt equals HTA T ambient minus T plus alpha I B. Okay, so let's go MC sub P dt equals, I plug in my nominal conditions. Okay, so let me just plug those in right here. HTA T ambient minus T plus alpha I B. And what do we know about this if I use steady state? If T ambient, T, and B, if those are steady state conditions. What do I know about this quantity right here? Okay, that's going to be 0. Okay, so I can just get rid of it. I don't even have to evaluate it. Okay, and the reason why it's 0, okay, if I say it's steady state, I know that this is 0. Okay, so if that's 0, I've just said I've plugged in my steady state condition, and I know my derivative of temperature with respect to time is 0, so that's why this is all 0. Does that make sense? Okay. Okay, so now I'm going to add this function right here with respect to TA first of all. So what does that equal? That's just going to be HTA. Okay, and then I multiply it by TA minus TA bar. Let me do the next one now. We do plus, and this is going to be a negative HTA, okay, times T minus T bar. Okay, and let me do the third one, and that's just going to be alpha I V minus V bar. Okay, and then I just define these as deviation variables. I put the little prime there. Okay, and those are my deviation d prime. Okay, so now I have m c sub p and then dt. Okay, and then I have HTA times TA prime minus HT A times T prime plus alpha I B prime. Okay, and what does that look a lot like, this linearized expression? What is that? So let's compare it to the original one. Does it look similar to that? Yeah, it's exactly the same. That's what I skipped over in class, okay? Because I knew for linear expression, you can just go directly put all your primes on it. Okay, but you probably want to go through that anyway, that process of doing a linearization anyway, even if you have a linear function, just to convince yourself that that's happened. Okay. What about this one though? I want to get this in terms of t prime as well. What do I do about the derivative? Okay, so let's just define that. T prime equals t minus t bar. Okay, and let me just solve for t. T equals t prime plus t bar. And then let me go ahead and just substitute that in there. Okay, and then if I do that, I've got t prime plus t bar. And then what do I know about what happens to that right there? That's a constant. Okay, yeah, it's just gonna equal dt prime dt plus dt bar dt, and that's gonna be 0. So I have, okay, I can just substitute in the t prime. Okay, but now let's see if that makes sense though. Let's see if that makes sense, because what we have is, let's say we have a function temperature. Okay, so let's say this is my temperature without, subtracting the nominal steady state condition. So let's say this starts at 70 degrees Fahrenheit. Okay, but what does my, if I say that 70 degrees Fahrenheit is my t bar, okay, where I started steady state conditions, what I'm going to do to get t prime then is just start at 0. Okay, and effectively just subtract off the 70 at every point in that trajectory, and that becomes t prime. Okay, and then this derivative, or the slope, at that point is that. Okay, if I go down, I have that same slope down here. I've just shifted it down, but the slope is the same wherever I am in that function. Okay, and that's why we can just substitute t prime in there. Okay, does that make sense? Okay, good. So let's go ahead and, now that we have this, let's go ahead and just take Laplace transform of it, and then get our transfer functions. Okay, so I'm just going to write that one more time down here. Equals HTA, and that is T ambient prime minus HTA, and then T prime plus alpha I V prime. Okay, so I'm going to take the Laplace transform of this expression. Let me just start with the left-hand side. Okay, so I have m c sub p, and then I have, yeah, that's right. So I have, yep, that's right, S T S. Okay, minus T 0, that's time domain, but that's going to be 0 because I'm in the deviation variable form. Okay, that's why we put it into deviation variable form. And then I have HTA, and then TAS minus HTA TS plus alpha I V of S. Okay, so I have, yeah, you normally just leave off the primes when you're in the Laplace domain because we know it's a deviation variable anyway, or a deviation variable form. So that's a good point. Yeah, why did we drop the primes? We normally leave off because we know. We assume that everything in the Laplace domain is in deviation variable form. Okay. Okay, so let's go ahead and just, so now we want to get back to the original question, which was get our transfer functions, v of s. Okay, so how do I get those from this expression right there? Okay, so let me bring it over. So this term, I know I've got to combine it with that term. I want to combine those two. So let me first of all just bring that over. Okay, so MC sub p s plus HTA, okay, times T of S equals HTA T ambient S plus alpha I V of S. Okay, so I've got that. Now how do I get these? Yeah, so first of all, let's just assume voltage is constant. Only the ambient changes. Okay, so what does voltage do? It's 0 because it's deviation variable. Yeah, that's right. So let's just assume, first of all, that this is constant. Okay, just that. And then let's get our transfer function. So we have T of S over T A of S equals HTA divided by M C P S plus HTA. Okay, and then let me assume that's not constant anymore. That's changing. And this is constant. Okay, and then I have T of S over V of S equals, alpha I, sorry. I started going down the other. Alpha I, M C P S, HTA. Okay, now we learned in class that you look at the denominator to determine stability and other things like that. What do you know about the two? I mean, the two denominators in this case are the same. What does that mean? Yeah, it has the same dynamics whether you have an ambient area change or the voltage change. It's going to get to the steady state. Affected by either one, it's going to get to the steady state. Okay, and it also means you can analyze stability for one and then kind of do the same for the other. Right. Okay. Okay, so there you have your two transfer functions. So what you'd want to do if you're doing this in Simulink, you'd have constant here. You have your V of S, and then you have your ambient air temperature. Okay, and then those would add together. Sorry, I need to do the transfer functions there. Okay, so you have this transfer function. I'll just call this one G2 of S, and this one G1 of S. Okay, and so this one would be which one? G1 of S and G2 of S, and then those could combine together to get your final outlet temperature. Okay, so if you don't have any ambient air temperature change, then you can just go with that one. And if you don't have any if you don't have any ambient air temperature change, then you just go with this would be constant, and you just have your regular transfer function between E and T. Okay, but you can add the output to those two. So you can have both things affecting your system at the same time, and you can just add the responses of both those together to get what the temperature is going to do with respect to time. Now, looking at the original equation versus our linearized model, our transfer function, how accurate is our linearized model going to approximate the real system? Okay. Yeah, so let's go back up to our equation. Let's say this is go back up to the original equation. This is our energy balance. And let's say this is very realistic. Okay, we derived it from first principles. There's no other conduction. All the assumptions are good. No radiative terms, things like that. How well is our linearized model? How well is it going to be able to fit that? Okay, you say perfectly. So why really well? Yeah, your nonlinear model, your first principles model is not nonlinear, it's linear. And so your linear approximations of a linear model are going to be very good. Okay, it's going to be right on. Okay, if that linear model does a good job describing that physical system. Okay, so let's think about you got a lot of constants here that you don't know, right? Mass, CCP, you got heat transfer coefficient, you have an alpha there. How do you get those? What's that? Okay, so yeah. Yeah, so let's get that into standard form. So great, yeah, let's do that. T AP tau P S plus 1, that's kind of our standard form. This is our gain, and this is our time constant. Okay, and let's get those into standard form then. Okay, so that's going to be, for this one, let's do G1 first of all. Okay, so G1 of S equals, okay, so that's going to be 1 over M C sub P over HTA S plus 1. Okay?
Yeah.
Yeah, so gain is 1. Okay, that's for your ambient air temperature. And then that is your time constant, tau P. Okay, and let's do it for the G2 as well. Okay, and that's going to be alpha I over HTA divided by M C sub P over HTAS plus 1. Okay, so that's your KP for the second one, and that's your tau P for your second one. Okay, so you can fit it from your empirical model, first of all, if you want to. Let's keep the first dead time model. And then just equate these constants to KP2 and these constants to tau P2. If you know a mass, if you have an estimate of mass, and it's 1 gram or something like that, you can plug that in. And if you know a heat capacity, you know, transistor, you've got multiple metals and other things going on with the transistor. So you just assume, you know, just make an assumption like this is steel, okay? Or you can say this is still, you know, whatever transistors are. You know, so you can make an approximation there. You know, just to try to pick out values, because what you want is a heat transfer coefficient. You can isolate that. You know, your area there is going to be an issue. So just go ahead and throw in best guesses for those numbers. You're not going to use that, but you can try to pick out different parameters that way. So let's think about the alpha term. How we can get the alpha term on our model? Okay, any ideas on that? How you can get the alpha term? So just think outside the box on this one. Okay, think outside the Arduino box on this one, and see if you guys can think about how would you go about getting an accurate estimate when you have 255 go into your Arduino. How would you guys know how much power is being dissipated over that transistor? Okay. Okay. Yeah, you can do that. Yeah, and so we tried to, you know, estimate it here. Let's just go back up to this equation. How could you change this equation right here? Okay, the one that I have in the box. How could you change that equation so that you can better isolate alpha? Okay, whatever temperature it gets to, good. Now, you also have a heat transfer coefficient. Let's say I wanted to not have to estimate heat transfer coefficient when I'm trying to estimate alpha, because there are two are going to kind of compete. You don't know which one. If the heat transfer coefficient is higher and the alpha is higher, you get more alpha dissipating it more quickly or not. What could you do to your system to try to isolate what is the value of alpha? Okay, so one idea is to make your ambient temperature equal to your transistor temperature, right? So you can have a superheater in your room, you know, try to follow the ambient temperature, try to follow that. So that would make this difference go to 0, and you could eliminate that term. Okay, how else could you eliminate that term then? Any ideas on that? How could you eliminate that, effectively eliminate that term, so that you can just kind of isolate all of them? How could you change your Arduino device so that you can make the area really, really small? Okay. Okay, so yeah, you could miniaturize your Arduino device. Okay. How else could you change it? And probably something that you could do in 5 minutes. Okay, without having to redesign a transistor. There you go. You could insulate it. You could just throw over some, insulate somehow. Maybe take some, I don't know, what would be a good insulator device?
Take the box.
Well, you'd have to heat up the whole box, So you want to just insulate that little device, so maybe wrap it around in a winter scarf or something. something that would insulate it. Maybe something that you could put over the top just of that little transistor device and insulate it. And then how could you determine, so let's do that. Let's just get rid of that term and just see what happens when we do that. Okay, so I'm just gonna take one that after we linearized it. Okay, and I'm gonna get rid of the HTA T ambient minus T prime. I'm just gonna say that's gonna go to 0 because we've insulated this thing. Okay, and then plus alpha IV prime. Okay, and so this is now, this whole term is 0. Okay, and let's go ahead and just take this over into the Laplace domain. Okay, S equals alpha I V of S. Okay, and then let's solve for our transfer function. Alpha I over M C sub P S. And then let's just give a step to our voltage. Start at 0, let's go up to 100. Okay, so what is V of S going to equal if I give it a step input? Okay, so it's for step input, it's 1 over S, but if I have a step of 100, it would just be 100 divided by S. Okay, so I just multiply that by 100. Okay, and then let's solve for T of S. Okay, so alpha I over MC sub P S times 100 over S. Okay, so that's 100 alpha I over M C sub P S squared. And then let's take that back into the time domain. Okay, so temperature as a function of time. What do I know about 1 over S squared in the time domain? Yeah, it's just a ramp, right? So I'm going to have 100, that's right, alpha I over M C sub P, and then that's just going to be times time. It's just going to be a ramp. So as I give my voltage input, step of 100, this thing is what the temperature is going to start ambient. Okay, temperature is a function of time. This is my voltage as a function of time. So does that make sense? If you eliminated any convective heat transfer, would you have a ramp for that temperature? Would it ever get to a steady state value? Or would it just continue to ramp? Unless it melted, yeah. If it's perfectly insulated and the heat can't go anywhere, and your heat capacity is constant, it's going to be a linear ramp going up. And what is the slope of that ramp? Yeah, so it's all of that. That's your slope. Okay? So if you know the mass, you know heat capacity, you know the current, you can get your alpha value from that ramp slope. Okay, so that'd be one way of doing it. So when people are constructing first principles models, they do creative experiments like this to try to isolate certain effects in their equations. Okay, so they'll do things like run at a really high temperature or really low temperature when they know certain terms are going to be negligible or cancel out. Okay, so that's just a strategy for modeling, trying to determine those parameters. And once you can determine those parameters in your model, you can change something like you can change your mass of your transistor. You don't have to go back and do all of your step responses. You can just change that parameter in your model, and you automatically have a very good dynamic model. Okay, so that's kind of the power of first principles model. So that's what I wanted you guys to, something similar to this, work through this. Now, let's say you had a radiative thing. We talked about that in class. How would you determine that significance? And what did you guys do if there were a radiative term?
Are you saying radiation in flux?
Well, if the temperature is high enough of your transistor that radiation term is significant compared to the convective term. Okay, so I'm going to go back to this original equation, okay, right here, and just add a radiative term. Okay, now I think it's something like this: T ambient minus T to the fourth, if that's radiation. Okay, so how would you deal with that when you linearize it? What would it change when you linearize it? Okay, so now it's nonlinear, right? Yeah, so how could you determine if this is significant for your system? Okay, yeah, there's some nonlinearity that you can't explain with your linear model. Okay, that might be one way to do it, because this is the only nonlinear term right here. Okay, and if your linear model is fitting your data very well, then it most likely means you don't have a temperature to the fourth in there that's significant. It's providing a significant heat transfer from the device. Okay, so and if you did include that term in your linearization, what terms here are going to change? Okay, so that's your constant A, that's your constant, well, that's an A as well. So this constant A would change. We'd have HTA times 4 times the emissivity, so all of that. You know what I'm saying? So you plug in the steady state conditions, but this would still be a constant. Okay, I'm just going to put A prime there. Okay, this would actually be a different constant. Okay, but you just have 3 constants out front. You'd have the same linear model, you just have 3 different constants out front, because you had an additional term that you had to linearize, and that contributed to that term out front. Okay, does anybody have any questions about that? Like if you want to add or do a model? Yeah, that makes it nonlinear. You have to linearize it for your homework. I think that's due today. You guys had that where you have to linearize your model before you can take the Laplace transform, because you have 2 variables multiplied by each other. Okay, so wind speed times temperature or something like that. Okay, so you got to linearize it so you can separate those variables, and then you can take the Laplace transform. Okay, good. So we kind of stepped through it in a lot more detail than we did in class. I've recorded this as well, so I'll just go ahead and take this and put it on and just go back and take a look at it later if you want. Any other questions you have about these two? Yeah.
When you do it, you actually have to implement that, like trying to not do
Well, yeah, just like we went through today, you probably want to talk about those things and talk about your assumptions and talk about, what terms you would actually need to put in. Okay, what have you guys noticed so far with fitting into a linear model? Is it pretty good on the first order percentile model? I'd say most of them that I've seen look like they are fitting very well. Okay, and so you could just say that, we considered the radiative term, but, our linear model is fitting this very well. What we would see, so tell me what you would see if the radiative term were significant. What you'd see is more heat transfer as the temperature grows versus decrease. Okay, so you'd see that your linear predictive model predicted a higher temperature than was actually the case at higher temperatures. Okay, because you don't have that radiative heat transfer away from the device. Okay?
So are we ignoring or saying conduction is negligible?
Yeah, we assumed conduction was negligible. So how would you test that one?
Is a conduction linear function?
Conduction's, yeah, linear function. Yeah, so that one's a little more tricky. I have to think about that as well. Okay. How you'd actually look at your data and try to infer what effects are important. with that. And it's the hard one. Okay. Okay. Yeah, so once you have these, I just wanted you to, so the assignment was to derive a first principles model between input voltage and output temperature, simulate the first principles model, and compare the results to the data that were selected during the doublet test, and then adjust the parameters to align the two. Okay, so you can first of all just start just with your best guess of heat transfer coefficient, your best guess of mass, CCP. Just try to put values in, simulate that against your simulated values of the device, and just see if they match up. If you're able to get your parameters pretty close, just with your best guess of the parameters. And then try to match them up like we did. So you try to pick them down, correlate that to alpha IO or HTA. And see if you can do that. Okay. I don't want you guys to spend a long time on this. I just wanted you to mostly go through the derivation, first principles model, compare it to the empirical model, and try to get your parameters to match up. Okay? Good. So, if you guys haven't run, so there's a couple things you guys need to run with your Arduino device. You need to run it to get your control set time model and get data for that, and then test your controller.